This is How to Math with Dr. Ian Lundholm. In today's episode, Infinite Series. And as you can tell, I'm going to try something a little bit different today. I'm going to use a PowerPoint slide deck, and hopefully this will make things a little bit faster in terms of my preparation so that I can make sure to get these lessons out to you on time. So, without any further ado, we're getting into Infinite Series. Here's a joke. A group of mathematicians walk into a bar. The bartender asks, "What can I get you all?" The first mathematician replies, "I'll have a beer." The second mathematician replies, "I'll have half a beer." The third mathematician replies, "I'll have a fourth of a beer." The fourth replies, "I'll have an eighth of a beer." And so on. The bartender returns with 2 beers. Outraged, one mathematician demands to the bartender, "How do you expect us all to get drunk off of 2 beers?" The bartender replies, "You guys should really know your limits." Get it? Limits? Hey, if you don't get it yet, you will by the end of this lesson. All right, 2 main topics for today's lesson. Partial sums, convergence and divergence. So we're going to be talking about infinite series, and those are infinite sums of things all added together. And next we're going to talk about, for point number 2, we're going to talk about geometric, telescoping, and harmonic series, which are all different types of series, but they are some of the most important types that we should start with. All right, so infinite series. We are adding an infinite number of numbers together, and we're going to use sigma notation for this. We've used sigma notation in the past when we learned the limit definition of the integral. But just to remind you all, this n equals 1 is our starting point. That's our first index. A to the n, that is, the nth term in our series. And then up here at infinity, that's where we end, or in this case, don't really end. We just keep on going forever. So, series and sequences are related because you end up adding together all of the terms in this sequence when you're working with a series. Let's keep going. This notation is technically formal notation because we use it to refer to the series even if the sum doesn't actually exist and actually, come out to one specific number. We talk about convergence and divergence again for series. And we're going to try to understand what it means to add infinitely many numbers based on the behavior of their partial sums. So we're going to look at the sum of just the first term, and then we're going to look at the sum of the second 2 terms, or the first 2 terms. That's a better way to say it. The first 2 terms, the first 3 terms, the first 4 terms, and pay attention to the sequence of partial sums. So if we have a series that looks like this, this sum where you cut it off at n instead of at infinity, that's the nth partial sum. Yeah. And we can, look at those partial sums as a sequence. It's going to make more sense when we actually look at a real example. And yes, we will talk about sequence of partial sums being convergent or divergent. That's just a little bit of notation. All right, example 1. We've got this infinite series, and I hope that you would be able to see that this infinite series would look like this. When n equals 1, we would have 1/2. When n equals 2, we'd have a fourth. When n equals 3, we'd have an eighth, and so on. And in order to determine whether this sum actually ends up being a number in the end and converging, or whether it ends up diverging to infinity or never really settling down and doing some kind of oscillating type diverging, yeah, we've got to look at the sequence of partial sums. So I'm hoping that this will get erased and we'll just be able to see yeah, the partial sums here. So first partial sum is just 1/2. That's just the first term. Second partial sum is 3/4, 1/2 plus a fourth. We add another eighth on for the third partial sum and get 7/8. Then we get to 15/16 for the fourth partial sum and 31/32 for the fifth partial sum. Now, what we're going to do is take 1/2, 3/4, 7/8, 15/16, 31/32, and treat them as a new sequence. So literally we're lining them up and using commas again. And just like the last lesson we did, we're looking at what does this sequence of partial sums converge to? And maybe once we write them out like this, you might notice that it looks like these partial sums, these fractions are getting closer and closer to the number 1, and they're not going over the number 1. So perhaps this is a monotonically increasing sequence that is bounded above by the number 1. And maybe after some thinking, you could come up with an explicit formula for the terms in this sequence. So, it's very similar to that sequence that we were looking at in the last lesson that actually converged. We're converging to 1, and we're getting closer and closer there. To show you what it looks like on a graph, this is what it looks like as n increases. Yeah. And here, if you were thinking this, great, but the partial sums always seem to be a power of 1/2 away from 1. So if I go back here, 1/2 is 1/2 away from 1. 3/4 is 1/4 away from 1. 7/8 is 1/8 away from 1. And so going back here, this is an explicit formula for the sequence of partial sums. And if we wanted to make that rigorous, we could use induction. And we could look and take the limit as n goes to infinity of our of our explicit formula and come up with 1. And that's great. The sequence of partial sums converges to the limiting value 1. And that means that this infinite sum, the one that started off, with 1/2 plus 1/4 plus 1/8, actually all adds up to 1 in the end, which there's not really an end. But yeah, that infinite number of numbers adds up to 1. And if you already checked out the Zeno's paradox video, hopefully that makes some sense. This kind of a question stumped ancient peoples, and they viewed it as a paradox for a long time. And yeah, it's not an easy thing to understand at first glance. All right, so with our first series out of the way, we're going to move on to the first major type of new series, which is called a geometric series. And the special thing about geometric series is that they have a common ratio. So if I wanted to, just write a geometric series, I could start with any number I want to, let's say 3. And then to actually create a geometric series, the common ratio that I might have, let's say the common ratio is 2. And in order to get the next number in the sequence, you would multiply by 2 and multiply by 2 and multiply by 2. That is a geometric type relationship. So very related to exponential growth. Here in this formula, A turns out to be our first term, and R is our common ratio. Whoa. Okay, cool. And now we got to think about, when would a geometric series converge or diverge? Well, I guess this slide gives it away. It only converges if the common ratio is less than 1. So basically, you want your numbers to be shrinking in absolute value over time. You want that common ratio to be small so that all of the terms in your series get smaller and smaller over time. And the geometric series diverges if the common ratio between successive terms is greater than or equal to 1. This is an important formula that you probably want to memorize. Honestly, the geometric series is that important. Actually, the ratio test that we will learn about later on is kind of based on some of the same logic as thinking about, how a geometric series behaves. Because we're always paying attention to the ratio between successive terms, and we need to make sure that ratio guides our terms down to being closer and closer to 0 towards the end. And the formula, the way that this works out in the end, is just a over 1 minus r. Here is just a proof of this last theorem, where we take a look at some of the special cases of geometric series. Here's what happens when a geometric series, the common ratio is 1. And weirdly enough, this PowerPoint is kind of bugging out, and it's going to happen anytime I use a PowerPoint, really. But this L just means ... So all we have here is a bunch of A's added together, whichever that first term A happened to be. But yeah, if your common ratio is 1, your first term remains just your term for every single term, and you end up multiplying A times N, and if N goes to infinity, the entire sum goes to infinity. So this would definitely be a case where the overall series diverges. If r equals -1, maybe we would have some more hope that maybe, I don't know, things cancel out and we end up coming to an actual number. But this is one of those things where, a lot like one of the sequences that we looked at earlier, this one oscillates between a and 0 as you go on, and never really settles down. It's oscillating in perpetuity. So again, we would call this divergent. And here are just a few lines of math that show you how the nth partial sum is derived in this kind of a case. So we're looking at the first n terms of our geometric series. Here we divide through, well, we multiply through by r. Yeah, we multiply through by r, so now this is an n instead of n minus 1, and, you know, there's an r over here. And then what we do is something tricky, but we subtract the two. Get back. We subtract, nope. There we go. Subtract the two. Get out of town. Here we go. We subtract 2, canceling out these terms. And so that all we're left with is a minus ar to the n power. Then we divide, or sorry, we don't divide. We use the distributive property on the left-hand side. And then we divide by 1 minus r. So this is a nice kind of explicit formula for the nth partial sum. And what we can do is analyze what does this expression do as n approaches infinity, because that'll give us a lot of insight into how the overall series behaves. All right, let's see. Shoot. This thing's not... Hey! There we go. Clear pen markings. Great. Now, this works out really nicely if the common ratio is less than 1. This term up here in the top right actually ends up going to 0 because that common ratio is small. And a small number to an infinite power just becomes smaller and, you know, approaches 0. So that's where we get this formula that kind of popped out of nowhere earlier. But if r is bigger than 1, then this term that I squared in blue, yeah, that one's going to go to infinity if r is big. And so that would diverge. So in conclusion, we're back here. We're back here. This geometric series only converges when the common ratio is less than 1. And yeah, that's what you want to memorize. Okay, example 2. We have a ball being dropped from an initial height of 8 h units onto a flat surface, and that ball bounces repeatedly. After each bounce, the ball rebounds up to a height that's r times its previous height, and so we've got a common ratio that is less than 1 because it's not going to bounce to exactly the same height that it started off with. But yeah, over in this diagram, you could see the ball being dropped, and then, the ball successively taking more bounces and getting a little bit lower each time. And right now, we're just leaving h as height, r as the common ratio, kind of the bounce factor for this particular bouncy ball. And yeah, we're gonna be fine. Our goal is to actually calculate the amount of distance that this ball has traveled over time in terms of its height. So all of the distance vertically, we want to count that in this problem. And we're going to actually, before I leave the picture, but we're actually going to use a pretty high bounce ratio here of 0.9. And if you've never seen it before, a steel ball on a steel plate bounces really, really high. If you haven't seen that before, I encourage you. Look up a YouTube video of it. It's really cool to watch. Two hard things, very, very bouncy together. So let's take a look here at some of the math. Here we're computing, looking at the partial sum. Well, yeah, I guess the total distance. Remember, this L is ... So yeah, this is... Shoot, I need a different color. This is our initial drop. This is the first bounce, second bounce, third bounce, and we're multiplying each one of these by 2 because there's a height on the way up and a height on the way down in terms of the distance traveled. And so this is a geometric series where the common factor is r. And so we do a little bit of changing down here. We wrangle this part together and turn it into the sum. Do a little bit of algebra, and we get to start analyzing this expression. This is kind of it solved in general, but if, say, the height is 5 meters and the bounce ratio is 9/10, then looking at how far this thing will bounce actually ends up being 95 meters from an initial height of 5. So that's pretty impressive. It's going to bounce many, many times with a bounce ratio of, 0.9. So that's pretty cool. All right. And I don't want to do number 3. We're skipping it. All right. Example number 4. Another cool application of a geometric series. Here we have the repeating decimal 0.293 repeating. And we can represent this as a ratio of 2 integers by using a geometric series. We can look at this sum, where if we're just going off of place value, the first 293 is 293 thousandths. And then if we shifted down the next 3 place values, we'd get this one. And then the next 3 place values would get this one. And so we have this infinite series. And we have an infinite series. Can you tell right now what the common ratio is and what the first term would be? Because those are going to show up right here. 293 over 1,000 is our first term, and the ratio is 1 over 1,000 because we continue to move down 3 place values. So we do a little bit of geometric series formula here and get 293 over 999. So that's really cool. Actually, you can make lots of repeating decimals that way by putting them over 9s. It's fun to play around with. All right. Now, we are moving on to telescoping series. And telescoping series are named this way because, like the pirates of old, with their telescopes that would collapse and extend, these series are going to collapse and extend based on their middle terms, which tend to cancel out, and the entire series tends to collapse. So let's take a look at example number 5. Here we've got this series, and we're going to be able to put our knowledge of partial fractions to the test and do some partial fractions on this one so that we could split it apart. All right. So that's looking good so far. Yeah, I mean, use your favorite partial fractions technique, maybe Heaviside cover up. But after you do that initial partial fractions, let's take a look at the first, three terms of this. First three terms look like this. And you may notice that the telescoping part of this is becoming apparent because while 1 doesn't cancel out with anything, negative 1/2 and 1/2 are going to cancel out. Minus 1/3 and 1/3 are going to cancel out. So on and so forth. There will be another 1/4 over here for this one as you go on. And that's the telescoping nature. What happens is that those tail terms cancel out, and you end up with an nth partial sum that looks like everything in the middle that gets canceled out except the first term and the last term. And when you take the limit as n goes to infinity of this one, well, we're just going to get 1, right? Yeah. So that series converges and has a sum of 1. So this is actually made up of parts here that wouldn't converge on their own. As we're going to see soon, this 1 over n piece is actually, just it by itself is the harmonic series, and by itself, it's actually going to diverge. But when it's part of a difference, like this, when it's, subtracted, the telescoping part ends up canceling out, and we get a nice number 1. Here we go for an important theorem. The terms of a convergent series go to 0. If this series converges, then the limit of the sequence of the terms must go to 0. So in order for this infinite sum to settle down, we need the terms in that sum to shrink, and shrink so much that they shrink down to 0 as n goes to infinity. That's, what it means for an infinite series to settle down. So this theorem definitely goes in this, forward direction. If we have this first condition, then we get the second one. It's not always going to be the case that just if we happen to have a sequence of terms that does end up going to 0, it doesn't necessarily mean that the overall series converges. So this, this theorem goes one way. Get out of here. There we go. Yeah, and honestly, I'm not really too interested in that. And this is just the converse. It's saying that if this limit doesn't exist or is different from 0, then it diverges. That's true. That's reading it in the other direction. But if your specific terms don't settle down to start approaching 0 as n goes to infinity, there's no hope for the overall sum to settle down. All right. Okay, so here is a good example. We're going to look at the harmonic series, and this is an illustration that even when we have this condition where the terms actually do end up going to 0, if we look at the harmonic series, we would start off with 1 over 1, then 1 over 2, then 1 over 3, 1 over 4, and so on. Those terms individually definitely do approach 0 as n goes to infinity. But this series actually ends up diverging, as we will see shortly. So let's take a look at this. What we do here, instead of looking at every single term in the sequence of partial sums, we're going to look at a certain subsequence of partial sums. So here's the first partial sum where we've got 1 over 1, or just 1. Here's the second partial sum. Here's the fourth partial sum. And at this point, it's nice to, compare what we've got. This part is the pure harmonic part. Oh, and there's going to be another one that comes up here. All right, harmonic. But we know that this harmonic part is actually greater than these, powers of 2 that we have here. So 1 plus a half plus another half gives us 2 in the end. And so this one, I guess we didn't write that out, is 3 halves. So our sequence of partial sums so far for this subsequence where we're only paying attention to the partial sums that have, a power of 2 in terms of the number of terms. We've got 1, 3 halves, and then 2. For the 8th partial sum, we've got another instance where this part up here is purely the harmonic part. You can see that, continues counting up. But we've already said that this part, the lower part here is greater than the upper part. Or sorry, the lower part is smaller than the upper part. So this 1/3 plus 1/4 is actually, greater than 1/4 plus 1/4. So this is another instance where we have a half. And here's another instance where the bottom piece is equal to 1/2. And so this part up top is bigger than 1/2. And, so here we've got 5 halves as a partial sum. And I think we go up to 16 here. Yes, we do. That one ends up equaling 3 overall, or 6 halves. And again, these L's are just ... dots. But what we're saying here is, let's take a look at the last group of terms here. We have 8 sixteenths in this piece, which is equal to 1/2. And we know that 1/16 is smaller than 1/9, and 1/16 is equal to 1/16. And everything in the middle, 1/16 would be smaller than a 10th, then an 11th, then a 12th. So again, we have that same relationship. We know that the partial sum here is going to be bigger than 3. And so in that case, as you look at this subsequence where we're looking at partial sums that have, an index of some power of 2, this is what the actual partial sum looks like. And as you take the limit as n goes to infinity, that sequence of partial sums goes to infinity. And so the harmonic series diverges. If you're curious, there are some really cool videos on 3 Blue 1 Brown. It's a YouTube channel that talk about the harmonic series. And actually, there's another series called Euler series, I think, that I might actually have you watch. So, yeah, that might come somewhere down the pike here soon. But yeah, if you want to go check out 3 Blue, 1 Brown, I'm sure that there's some cool stuff to check out there. All right, here's a theorem very similar to the limit laws that we looked at in 10.1. Here we've got sum, difference, constant multiple law. This only works when we have 2 convergent series. Both of those need to be convergent. If one of them is divergent, then this sum law, I mean, you could still break up the series like this, or combine them together, whichever way. That's kind of just the I don't know, associative property of addition there. But we wouldn't say that the overall sum converges unless both of the individual sums converge as well, both of the individual series. Okay, so example time. We're going to example number 7. We're going to take a look at both of these series and determine whether it converges or diverges. This first one, it's got 2 to the n in it. It's got 4 to the n minus 1 in it. That makes me think that this is going to be somewhat geometric, that somehow we're going to be able to find some common ratios here. And probably the common ratios over time will look, pretty similar to 1/2, because that's the ratio that we see there between 2 and 4. All right, so let's rewrite the terms of that series in a more useful form. Just breaking apart the top there. And then we are getting the n minus first powers lined up here. So we pull out this 2 from the 2 to the n. And so we get this sum, where all these first parts, have a common ratio of 1/2, and then the second parts have a common ratio of 1/4. Let's see how this goes. Both of those individually are geometric series that would converge. So we know that the original series converges. That's what this sum law meant. If you know that you've got 2 convergent series and you add them together, you know that the overall series converges. What's interesting, though, is the way that this problem has been cooked. When you actually end up working out the geometric series here using that formula, the bottom part of the first one ends up being 1/2, and so you've got 2 times 2 here. And then down here you've got 1 minus 1/4, and so that denominator ends up being 3/4, or you're multiplying 3 times 4/3, and you end up getting 4 minus 4, which is equal to 0. And so, I don't know, that was kind of anticlimactic, but yes, indeed, that first series converges, and it makes some sense because the first term here is -1, and then all the rest of this ends up being 1 and canceling out with the first part. Well, yeah, include the ... There you go. All right, and for the next one, hopefully we can get it here. We've got this n plus 2 over n times n plus 1. We use partial fractions again and decompose that. And this looks very, very similar to the telescoping sum that we had earlier. The telescoping sum, I think, was only different in that there was a 1 there instead of a 2, but that's actually going to make a pretty big difference. If we took both of those apart, just looked at this series by itself and this series by itself, both of those would diverge. The first is just 2 times the harmonic series, which we just proved diverges. And the second one is the harmonic series with the first term omitted, but that would still end up diverging towards infinity. And so we have this, we have this difference where both of the individual series would diverge. There's still some hope that the overall thing could converge if there's lots of cancellation, like in that telescoping series example, but not enough actually cancels out this time. So let's take a look at this. It actually ends up being that telescoping series plus the harmonic series. And if you add, infinity plus 1, you still have something that diverges. So let's take a look at what happened. Stop it. All right, this thing's not behaving. Please. The power of Christ compels you. Okay. We have also arrived at this immediately if we So there's an alternate way of decomposing that fraction at the beginning that would get you to the harmonic series plus a telescoping series thing. But yeah, we are going to diverge. So yeah, what this is trying to say is, in order for the whole convergent sequence plus another convergent sequence equaling a convergent sequence or series to work out, we would need this to work out. But this is one of those things that just doesn't work out because, this guy is the harmonic series and it's not convergent. I think it's a little bit more reasonable just to look at it this way and say, hey, we've got a harmonic series and we're adding something onto that, but that something is, finite. So overall, we're diverging in this case. But it wasn't immediately obvious at the beginning. All right. In example 8, we get a little bit creative and look at some problems that have some weird starting points. We're starting off at n equals -2 there and n equals 3, but these are just going to be geometric series, right? It's a little bit of investigation to figure out what the starting point is. So for that first one, you could literally just start by putting -2 into the exponent and getting 9. And that's probably the easiest way to do this, because then you can just use your formula and say, 9 over 1 minus -1/3, which is the common ratio, and get your sum in the end. It converges to 7 over 4. So that one's not too bad. The next one, you can see that the common ratio is 1/5, and the first term is 2 over 5 to the 5th. And so it ends up converging to 1 over 1,250. So, I don't know. Those were 2 geometric series. Nothing too difficult there, just starting off at a different index. And that's the end of the show. I hope it wasn't too bad to do the PowerPoint overall. It definitely saves me time in terms of preparation so that I can, focus on churning out videos rather than creating entirely new notes before creating the video. So if you have any questions, please seek me out on Pronto. I would love to see you there. We can work on online homework. You can ask questions about how this whole online class thing is going to work. Um, you may have seen that in the schedule, I recently put in some new days for just office hours. I think we're going to need to slow the pace of the class a little bit just for our online format, doing 4 days a week and getting... Here, let's change this real quick. Let me go to Spring 2020 and then find your syllabus while I'm thinking about it. Here we go. I'm out in the shed, so the Wi-Fi's a little bit weak. Come on, shed Wi-Fi. Come on, shed Wi-Fi. Please. Well, anyways, what I was saying is that instead of doing 3 lectures in a row, then activity, then homework, and continuing those vicious cycles, I've thrown in some more days for just office hours where we can, digest what we're doing, where we can work on online homework together, and just have a little bit more chill to the pace of the class. I'm hoping that everyone's agreeable with that. I don't think that we're going to be able to get into Chapter 11 in this format, but that's okay. We'll start in Chapter 11 in Calc 3. There we go. Good grief, shed Wi-Fi. All right. So here, oh goodness. Here's a tentative schedule for the rest of the semester. Let me know what you think. If I have made any errors in my rush to get our class online, I would not be surprised. And right now, I'm thinking that we try to do an exam once, and it ends up happening here at the end of, the final week of classes. And I give you guys some time to do it, and probably, more than one attempt to do it, especially if we're doing something online. I want you guys to have multiple attempts at working it because, Hawks can mark it wrong when you just, miss one little thing. You can do a sign mistake or something and you get marked wrong. So I think our final exam will not be worth as much as it initially was, and we're not going to necessarily have an exam 2 and an exam 3. So a lot of the exam grades for this term are, becoming smaller or non-existent, which should be a good thing overall for your grades, as long as you are, doing the online homework, doing the written homework, and making sure that you're doing the activities along the way. You should be good. I have activities posted to Canvas now. And homework solutions will be posted to Canvas along the way as we do that. And if you have any questions about how that's going to roll out, please use Pronto. Envision Pronto as kind of like our classroom away from the classroom. I would like the majority of our communication to happen there so that I don't have to answer the same question multiple times via email. But yeah, I know it's a little bit awkward to, chat in front of your classmates, but we'll get used to it. And I think having that sense of community will be a positive thing for us as we are separated by distance. All right. This has been How to Math with Dr. Ian Lundholm. Remember, you have online homework to do, and now you're ready for it. I'll see you in the next one. Have a good day.